first of these laws that we're going to look at is known as Boyle's law. With Boyle's law, we're going to look at the relationship between volume and pressure. What that also means is that anything else, so for example, temperature and number of moles, we will assume constant. Now, one of the things we can do to help ourselves with any of these gas laws is to think intuitively about what these gas laws are saying. So if we consider the two terms that we're going to look at in Boyle's law, volume and pressure, what is the relationship between those? In other words, if you increase the pressure on a gas, what will that do to its volume? Well, increasing the pressure pushes in on the gas, it compresses it, and so if your pressure goes up, your volume is going to go down. And the opposite would be true as well. If we decrease the pressure, then the volume goes up. So we can say that for a gas, the volume is proportional to 1 over the pressure. And so the initial form of the equation that we use, or that we'll look at, is volume is equal to some constant K over the pressure. The challenge with this equation is this constant K. This constant K is unique for every gas. So that means if we want to use this equation, at least in this form, we'd have to have a huge table full of Boyle's law constants. And if we encountered a new gas, then we'd have to figure out how do we determine K for that gas. So we actually use Boyle's law in a different form from what we have written here. So if we consider some gas under some set of conditions, P1 and V1, that'll be equal to that constant K. If we take that same gas and change the pressure to some new pressure, P2, the volume will change in response to some different volume, V2. But as long as these are the same gas, the product of P and V will be equal to that same constant K. Since these are equal, we can just substitute and do away with this constant entirely. And so the form of Boyle's law that we'll use, much more useful form, just says P1 V1 equals P2 V2. And as we go through the next couple of equations, we'll see that it's going to be the exact same thing as we change and look at different variables. So this is your first important equation in this chapter that you'll want to remember. Our next gas law is Charles' law. Charles' law, we're now looking at constant pressure. And still a constant number of moles. So that means what are we looking at here? We're now looking at volume and temperature. So again, we want to think about just what we know about gases before we write anything else down. if we have a gas and we increase the temperature, that means the gas will expand. The volume of the gas will get larger. So if T increases, V increases as well. So we can say that volume is proportional to temperature, or V equals K times T. Now we run into the exact same problem with Charles' law with this constant that we did with Boyle's law. This constant is different for every gas. So we can do the exact same rearrangement and substitution. We're going to first isolate K by itself. So K is equal to V over T. And then by using two different sets of conditions, we can say, and this is our useful form of the equation, V1 over T1 equals V2 over T2. And that's our useful form, or the form of Charles' law that you'll need to know. Now we haven't talked about units yet, so let's go back to Boyle's law for a moment and talk about units. What units do we use in this equation? Because for some equations, we have to use a very, very specific set of units. For Boyle's law, that's not the case. The only thing that matters is that we're consistent. In other words, whatever unit we use for P1, we have to use for P2. Same thing for volume. We can use any unit we want here for volume as long as we use the same unit on both sides of the equation. When we look at Charles' law, that remains true for our volume units. V1 and V2 can be any volume that we want to be. It's just they have to be the same unit. If they're not the same unit, the equation doesn't work. Temperature is different though. When it comes to temperature, our temperature has to be in Kelvin. Recall that Kelvin is basically just a recentering of the Celsius scale. To get to Kelvin, we take degrees Celsius and add 273.15. But we have to do this because if we use Celsius, that would mean we could have negative numbers in our equation. Well, if we have negative numbers in this equation, that would mean it would be possible for volumes to be negative. If you think about what volume is, that's not something that can be negative. So we have to keep this in Kelvin in order for our math to work. All right, so Boyle's law looked at constant temperature. Charles' law, constant pressure. That means we're going to have a third one that looks at constant volume. And that's known as Gay-Lussac's law. So for Gay-Lussac's law, we're going to consider pressure and temperature and constant number of moles and constant volume. So again, I want you to just think about what is the relationship of temperature and pressure for a gas. What happens if you increase the temperature of a gas? Well, we said with Charles' law that would increase the volume. But if we have a constant volume, then the gas might want to expand its volume, but it can't. So in that case, pressure will increase. So you may hear that you're never supposed to heat a closed system. This is why. If you heat a closed system, pressure increases, continues to increase, And if it increases enough, it can cause your closed system to explode. But what we end up with here is that pressure is proportional to temperature, or that pressure is equal to K times T. Same thing as with Charles' law. We're going to rearrange, we're going to substitute, and then we get the form of this equation that we can use that gets rid of that constant. P1 over T1 equals P2 over T2. And that's the form of this equation that we will find that we use. Now, we can combine all of this together into what is maybe not so creatively referred to as the combined gas law. The combined gas law, P1 V1 over T1 equals P2 V2 over T2. And you can see it incorporates all three of these equations together: Boyle's law, Charles' law, and Gay-Lussac's law. In fact, when you look at this equation carefully, you can actually use this to derive the other three equations. What do I mean by that? So here's our combined gas law. Let's say we're dealing with the conditions of Charles' law. Charles' law recall, has constant pressure. Well, if pressure is constant, that means that P1 is equal to P2, which would mean that we could cancel those terms out. What are we left with then? V1 over T1 equals V2 over T2, which is what we defined as Charles' law. And you could do the same thing for the other two laws, constant volume or constant temperature. So now that we've got these basic laws down, we've got these equations, we're going to do some practice and see how we use these. So our first problem says the gas inside a balloon has volume of 28 liters. And that's at a pressure of 2.3 atmospheres. What is the volume at 1 atmosphere? So first thing we want to identify, what equation are we using? So we have pressure, different pressures, and we have volumes to look at. That tells us we should be looking at Boyle's law. P1 V1 equals P2 V2. Now, is it important that you know the exact names of these laws? Not really. If you know how to use them, that's what the critical thing is here. So when I do these, I like to think of our P1 V1 as our initial conditions, where we start, and then P2 V2 as where we're ending. But if you switch them, reverse them, it won't make any difference. But if we do it the way I just mentioned, then our P1 2.3 atmospheres times our volume when it was at 2.3 atmospheres was 28 liters. And that's equal to some new pressure, 1 atmosphere, times V2. And V2 is what we're trying to figure out. So we just need to do our math here, solve for V2. And before we ever put anything into our calculator, we always want to think about, does the answer we get when we do this calculation, does it make logical sense? And so in this case, what's our change? Our change is in pressure. Pressure has gone down. And what did we say about the relationship of pressure and volume? We said they're inversely related. So if pressure is going down, what should happen to the volume? The volume should increase. And that's what we find when we do this calculation. New volume, 64 liters. All right, let's do another one. So a gas has a volume of 720 liters. And that's at 740 millimeters of mercury. What pressure is needed to reduce the volume to 175 liters? So pressure and volume, again, we're going to be dealing with Boyle's law. Now, in this case, our volume is decreasing. Oh, and I want the pressure, I want our answer here to be in atmospheres. So our volume is decreasing. So what has to happen to our pressure? Pressure has to go up. So P1, 740 millimeters of mercury, times V1, 720 liters, is equal to, our new pressure is unknown, times our new volume. So what do we get for our new pressure here? We get a new pressure of 3,040 millimeters of mercury. However, we're not done, because our question here asked for the pressure in atmospheres. So now we just need to do a unit conversion. 1 atmosphere is 760 millimeters of mercury, and we get an answer of 4.01 atmospheres. So as we expected, in order to decrease the volume, we have to increase the pressure. All right, let's do one more of these. And this last one right now is going to be more complicated. So we're going to start with a sample of some gas, and in this case we'll make it argon. But notice about this problem, the identity of the gas doesn't actually matter. And that sample of argon has a volume of 65 milliliters at 22 degrees Celsius and 750 torr. And if you think about these conditions are pretty normal conditions. 750 is just a tiny bit below standard atmospheric pressure, and 22 is a reasonably comfortable temperature. So now we're going to take this sample of gas, this 65 milliliters, and we're going to take it to the surface of Pluto. Where, as you can imagine, the conditions are quite different. The temperature, negative 380.5 degrees Fahrenheit, and the pressure, 1 Pascal. So our question becomes, what happens to the volume of this sample of gas? Now let's look at our two items. So our temperature is decreasing. In fact, our temperature is decreasing quite significantly. Now, if the temperature goes down, that'll make the volume smaller. The pressure is also decreasing, but that'll increase the volume. So at this point, we might not have a good guess on which way our volume is going to go. So I like to do the following to help set up a problem like this. Given that we're dealing with pressure, volume, and temperature, this is going to be a combined gas law problem. So P1 V1 over T1 equals P2 V2 over T2. So let's line up all of our numbers and see what we have. P1, our initial pressure, 750 torr. Our initial volume, 65 milliliters. And our initial temperature, 22 degrees Celsius. Our second set of values, P2, 1 Pascal. V2, that's what we're trying to determine. And T2 is negative 380.5 degrees Fahrenheit. So we've got a few things that we're going to need to do before we can actually do this calculation. First item is our two pressure values are in different units. So we need to pick one. Second thing is neither one of our temperature values are in Kelvin. So we need to convert those to Kelvin. So let's grab this table here that I've made and take that over here. And see what we can do. T1 is our easiest conversion. Going from Celsius to Kelvin, we just add 273.15 or 295.15 Kelvin. Our T2 is going to be a little bit more complicated because this is in Fahrenheit. How do we go Fahrenheit to Celsius? So Fahrenheit to Celsius We subtract 32 and multiply by 5/9, which gives us negative 229.2 degrees Celsius. Of course, we do need to go a step further and go to Kelvin. So we're going to add 273.15 to this, and we end up with 43.98 Kelvin. We also need to do a pressure conversion. We have pascals on one side, torr on the other side. Unless you like working with a lot of decimal places, it's going to be easier to go from torr to pascal. So our conversion here, 101,325 pascal is 760 torr, and that calculates out to just shy of 100,000 pascals. So now we've got all of our units in places that they need to be. We've got the correct units for temperature, and we've got both of our pressure units in pascal. Now we can do our calculation. So our P1, again, that's what we just calculated, times V1, 65 milliliters, over T1, is equal to P2 times V2, which is our unknown, times T2, 43.98 Kelvin. From here, we solve for V2. And now we might be able to make a guess as to which direction the volume is going to go. There has been a definite decrease in temperature, but you can see it's only about 6 to 7 times, or 1/6 to 1/7 of the original temperature. Whereas the pressure has gone down by almost a factor of 100,000. That means the pressure is probably going to be the more important change here. And that's what we find when we do this calculation. Our initial volume of 65 milliliters under these different conditions has become 970,000 milliliters.